In this video, we will discuss various methods for drawing structures in organic chemistry, including Kekulé structures and bond line structures. We will also cover how to draw these structures from a given molecular formula and how to draw different isomers of a compound. Up till now, all of the structures we've seen have been Kekulé structures. Kekulé structures are a way to represent the molecular structure of an organic molecule using lines to show chemical bonds between atoms. In these structures, each atom is drawn in as its elemental symbol, such as oxygen being O and methyl groups being CH3 in dimethyl ether. In these structures, we can omit the non-bonding electron pairs for simplicity, but it's important to remember they are still there. Oftentimes, organic chemists don't want to spend the time drawing each atom in a molecule. We can get around this by drawing a bond line structure of a molecule, also called a skeletal structure. These structures are a representation of molecular structure, in which covalent bonds are represented with one line for each level of bond order. Another important feature of bond line structures is that, along with non-bonding pairs, hydrogens bonded to carbons are often omitted as well. This is done for simplicity, but once again, it is important to recognize that hydrogens and non-bonding electron pairs are still present. Here are the Kekulé structure and bond line structure of the same molecule, isopropyl alcohol, drawn side by side for comparison. Notice that each vertice represents a carbon atom and that the geometry of the central carbon atom is preserved. Here are a couple molecules drawn in bond line form. Try to observe the patterns we just discussed in these molecules. Now let's discuss how to predict a molecule's structure from its molecular formula. When given a molecular formula, it's helpful to start by calculating the molecule's degrees of unsaturation. As we discussed in a previous video, the degrees of unsaturation can provide valuable clues about the presence of ring structures or multiple bonds in the molecule. By now, you may recognize the following molecular formulas, CH4, C2H6, and C3H8, as methane, ethane, and propane. These alkanes have only one possible structure given these molecular formulas. But what about butane? Butane is a 4-carbon alkane with the molecular formula C4H10. Judging by how we have seen propane drawn in bond-line form, it's reasonable to believe butane looks like this. While this is a correct structure for butane, it isn't the only structure that can be drawn that matches its molecular formula. Butane can also be drawn like this. N-butane and isobutane are isomers. This means they have the same molecular formula, but have different arrangements of atoms in space, leading to their different chemical and physical properties. More specifically, these molecules are constitutional isomers, or molecules with the same molecular formula, but different atom-to-atom connectivity. Alkanes with 4 or more carbons all have multiple constitutional isomers. Let's walk through a strategy for drawing all the constitutional isomers of pentane, for example. First, we identify the molecular formula and calculate degrees of unsaturation. In this case, we're working with an alkane, so the degree of unsaturation is 0. Next, we will determine the possible carbon skeletons starting with the straight chain form of pentane. From there, we can begin drawing branched chains. Finally, we check for redundancy and make sure that all the structures listed are unique and represent different connectivities of the carbon atoms. For example, these two structures are the same molecule and don't count as different constitutional isomers of pentane. This 3-step process tells us that there are 3 constitutional isomers of C5H12, which are N-pentane, 2-methylbutane, and 2,2-dimethylpropane. The N in N-pentane stands for normal and refers to the straight chain version of pentane. We will discuss the naming conventions of the other 2 isomers in a later video. Now let's examine molecules with 1 degree of unsaturation. There is only one way to draw ethylene, C2H4, and propylene, C3H6. So these molecules do not have any constitutional isomers. However, say we label each of the hydrogens in ethylene 1 through 4. Let's draw another molecule of ethylene except hydrogens 1 and 2 are substituted with chlorines. We will call this molecule A. Now let's do the same thing except hydrogens 1 and 4 are now substituted with chlorines. We'll call this molecule B. And finally, let's do it one more time except hydrogens 1 and 3 are substituted with chlorines. We'll call this molecule C. Both A and B have the same molecular formula, C2H2Cl2, but their atoms have different arrangements in space, so therefore they are isomers. However, they do not differ in atom-to-atom connectivity, so they are not constitutional isomers. A and B are stereoisomers, isomers with the same atom-to-atom connectivity. A is cis-1,2-dichloroethylene because the two chlorines are cis or on the same side of the double bond, and B is trans-1,2-dichloroethylene because the two chlorines are trans or on opposite sides of the double bond. A and B are stereoisomers, and C is a constitutional isomer of A and B. As always, let's do some practice. Draw all possible structures that fit the following molecular formulas and identify the relationship between these structures. Feel free to pause the video and try these problems on your own first. Before we begin drawing structures, let's quickly calculate the degrees of unsaturation for this hydrocarbon. Recall our equation. Degrees of unsaturation equals 2C plus 2 plus N minus H minus X all over 2. We have 6 carbons, 14 hydrogens, and no nitrogens or halogens. Plugging these values into our equation, we get that the molecule has 0 degrees of unsaturation. More specifically, we're working with hexane, a 6-carbon alkane. Recall that alkanes with 4 or more carbons have multiple constitutional isomers. Let's draw all the constitutional isomers of hexane. We can determine the possible carbon skeletons starting with the straight chain form of hexane. From here, we can begin drawing branched chains, decreasing the parent chain by 1 carbon at a time. Finally, we check for redundancy and make sure that all the structures listed are unique and represent different connectivities of the carbon atoms. There is no redundancy in the structures, so these are the 5 constitutional isomers of hexane. Moving on to the next question. Once again, before we begin drawing structures, let's quickly calculate the degrees of unsaturation for this hydrocarbon using our same equation. We have 4 carbons, 8 hydrogens, and no nitrogens or halogens. Plugging these values into our equation, we get that the molecule has 1 degree of unsaturation. We know that molecules with 1 degree of unsaturation can have a double bond or a ring structure, and in this case, we're working with a 4-carbon hydrocarbon where both of these are possible. We can start by first drawing the straight chain form of the hydrocarbon. Now we can draw in the double bond in 4 different ways, giving us 4 structures. Let's label these structures A through D. Once we run out of unique structures for the straight chain, we can move on to branched chains. There is only one possible way to add the double bond into our branched chain, which gives us this structure. We can label this structure E. Next, we can draw the possible ring structures that satisfy this molecular formula. The first ring structure we can draw is the 4-membered ring, cyclobutane. We can now decrease the carbons in the ring by 1 and draw methyl cyclopropane. We can't form a ring with anything less than 3 carbons, so these are our only ring structures, which we will label F and G. Finally, let's check for redundancies and identify the relationships between these structures. Structures A and D are the same molecule drawn slightly differently, so we can cross out one of them. All of the remaining structures are isomers of each other. Structures B and C, cis and transbutene, are stereoisomers and constitutional isomers of the other 4 structures, and the other 4 structures are all constitutional isomers of each other. As always, thank you for watching, and I'll see you next time.